Hi everyone, in today's lesson we are going to start chapter 7, and 7.1 is going to introduce the concept of continuous random variables. We are going to kind of get back to probability distributions. We're going to mix that a bit with statistics, and we're going to talk about a very important type of probability distribution that's used in statistics called the normal distribution later in this chapter. But for now, we're just going to introduce continuous random variables. You may remember from chapter 4 about discrete random variables. So we're going to do continuous random variables now. And if you remember the difference between the two, a discrete random variable is a variable that can only have certain values. It is countable. But continuous random variables is a variable that can have infinite number of possible values within a given range, like an infinite number of decimal places. So common examples include time, height, and distance. So when you think about time, for example, time can always be broken up into smaller and smaller units. Same with height and distance. All right. So now representing continuous random variables is slightly different. There are an infinite number of data values between any two data values. So what we need to do is we have to represent them in terms of intervals. Okay, we cannot just give one exact value. Now, the types of ways we can display, represent continuous random variables can include an interval table, a frequency histogram, a frequency polygon, or a probability distribution graph. We're going to cover tables and frequency histograms and polygons now. Simple example. Example 1 says 20 AA batteries were tested for their battery life. The table shows lifetimes of each battery when tested in a game controller, rounded to the nearest hour. So these 20 numbers around here represent the hours for each battery when tested in a game controller. So remember, here we're looking at time, right? The life of a battery is measured in time. So these are continuous random variables. Use an interval to determine the frequency of each table. Set values for each interval at 5-hour increments, starting at 20. So starting at 20, I can count how many there are within each interval. So for 20 and 25, I see 2. For 25 to 30, I have 4. For 30 to 35, there are 7. And for 35 to 40, there are 5. For 40 to 45, there are 2. Now, we can use this information now to draw a frequency histogram and add a frequency polygon to the histogram. Okay, so our histogram, again, you're going to have a positive axis, a vertical axis, and a negative, not negative, a horizontal axis. Frequency and lifetime in hours. All right, so we can start at, say, 15 here, 20, 25, 30, 35, 40, 45, and 50. Okay, so we can have like that. So 20. So let's do our, see, maybe 1, 2, 3, 4, 5, 6, 7, 8, like so. All right, so let's draw our bars now. 20, 25, we had 2. Okay, so let's go up here like so. 25 to 30, we had 4. 30 to 35, we had 7. 35 to 40, how many were there? We had 5. 40 to 45, we also had 2. Okay, so it's going to look a little something like this. Now, the frequency polygon should give you an idea of what the shape would look like if you were to break down the intervals into smaller and smaller sizes. So if we were to have many, many bars and a very, very large sample instead of just 20 batteries, the frequency polygon will tell us the general direction that the shape will take. So how you draw a frequency polygon is you got to connect the midpoints of each bar. So it's right here, 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 and here. And then we have to connect them to the horizontal axis by pretending that there's another interval to the left and the right and connecting the midpoint of that, like so. Okay? Then we can use lines to connect them. All right, so this right here is a frequency polygon. All right, so that's a frequency polygon. Okay, so those are the basics of how displaying continuous random variables work. Next, let's look at one of the possible probability distributions for continuous random variables. It's the same as a discrete random variable probability distribution, and that's the uniform distribution. If you remember, the uniform distribution is one where the probability of every outcome is equal. So if the intervals are the same, then the distribution is likely to be uniform. So get a very simple example. Say which distributions are example of uniform distribution. So here, this would be uniform, right? Because the probabilities are the same for each 5-minute interval. Okay. Sorry, this should be 6 instead. 6 to 10. Now, next up, we have B, and the probabilities are not the same, so this is not uniform. Okay. Actually, we do have one correction we need to make here. We should write 5 to 10 here, and this should be 10 to 15, 15 to 20, and 20 to 25. This can be 10 to 20, 20 to 30, 30 to 40, and 40 to 50, like so. Okay. Now, some of you may be wondering, okay, so for the first one, if I had something that was 10 minutes, does it go in the first interval or the second interval? That's a good question. The thing is, based off continuous probability distributions, it is not possible to have a time that's exactly 10 minutes. So we would have to put it in one of those two intervals. Okay, so going back to example 1, example 2C asks, from the table in example 1A, does that show a uniform distribution? Yes or no? So obviously the answer here is no. Okay, the frequencies are different for each interval. All right, so for the histogram of uniform distribution, it's actually quite simple. The shape is basically going to look like a rectangle, just like what it looked like for the discrete random variable probability distribution. Right? Now the vertical axis, instead of being called probability, is the probability density. Okay? And the probability density is just 1 divided by the length of the whole interval of the random variable. That's because the area of the histogram should equal to 1, right? So if the interval is, say, 40 minutes, then the height is 1 over 40, so that 40 times 1 over 40 is equal to 1. Okay, example 3 says, the time it takes for students to answer a particular question on the test varies from 1 minute to 5 minutes. Sketch a probability distribution graph for this distribution. So, like so, it's the probability density. So we can just sketch something very, very basic. Okay, so this right here. Okay, so time in minutes is going to range from 1 to 5. Now, this here has a length of 4, right? 5 minus 1. So if you want to look at the formula, it'll just be 1 over 5 minus 1, which is 1 over 4. Okay, so that's how you get the probability density. And that's pretty much it for the probability histogram for uniform distribution. All right, so to find the probability of an interval in uniform distribution, you just have to find the length of the interval and then multiply that by the probability density, right? Because remember, the area represents the probability. So going back to this example, what's the probability that a student will take 2 to 5 minutes to answer the test question? So the probability that I'll take 2 to 5 minutes will just be 5 minus 2, which is the length of the histogram, right, times the height, which is 1 over 4, aka 0.25, so 0.75, 75%. C, what's the probability that it will take a student exactly 3 minutes to answer the question? Okay, so we didn't quite talk about this in detail, but okay, the probability of any one exact data value in a continuous probability distribution is 0. Now, why is that the case? Remember the definition of a continuous random variable. There are an infinite number of data values in between any two data values, right? Because we can have infinite number of decimal places. So that being the case, that means the sample size is basically infinity. So one possible outcome divided by infinity is basically approaching 0. Okay, so the probability of any one exact data value in a continuous random variable probability distribution is equal to 0.